So consider a problem where you have a piece of putty, which is a point mass, coming toward a rod pivoted about one of its ends at point P. The rod, for simplicity, I've taken to be the same mass as the putty, little m, and the length of the rod is little l. Now the putty will stick to the rod and cause the rod to be swung by a certain angle. So let's denote that process here. That angle is going to be some maximum angle, which I'll call theta naught. Okay, that angle theta naught is something that we have to find in the process of determining the purpose of the problem, which is to write the equation of theta as a function of time after the collision. So after colliding, it's going to go up to a certain angle, and then it's going to swing back, and it's going to do this back and forth. Well, we're going to assume that theta naught is small. And I put small within quotes because you really have to say small compared to what. So we're going to assume it's small in the sense that sine theta naught is approximately equal to theta naught in radians. That's the meaning of small angles. And you can actually specify precisely what you mean by that. Is it 5% off or is it 10% off? That I'll leave, the details I'll leave to another time. So let's try to find this. First of all, you're all pretty expert at what's conserved and what's not conserved in a collision. In this collision, energy is not conserved during the moment of collision, but linear momentum is not conserved because you have this external pivot force that kicks in, F sub P, the moment you have the collision here from all those problems that we did of a similar nature before. So the only thing conserved during the collision is angular momentum. So let's do that first order of business. Sum of the initial angular momenta about the pivot equals the sum of the final angular momenta about the pivot. Now, the initial angular momentum about the pivot can be best found when this is about to hit. Then it's going to be the linear momentum times the length, okay, because it's r cross p, right? So it's linear momentum times the length times sine of 90 degrees. So let me write that. mv naught L sine 90 degrees. And that should be equal to the rigid body moment of inertia times angular speed. Let's call this the initial angular speed. I'll call this omega naught. So I'll get the moment of inertia of that uniform rod is 1/3 ml squared, standard moment of inertia table entry, that is. And then the putty is located at distance L, and the putty is a point mass, so that gets an ml squared times the initial angular velocity omega naught. So I lose one factor of L here, and I also lose the m's. So let's see what I have. The other factor of L can come down over here. So V naught over L, sine 90 is 1, so I won't write it. 1/3 plus 1 is 4/3. So that becomes 3/4 when you bring it over here. So that gives me the first thing I need. Now once you have the collision, the next thing that happens is the initial kinetic energy becomes the final potential energy. Now for this, again, I've done problems of a similar nature before. You have to use what's called the pendulum geometry. There's two pendulum geometries here, one associated with the center of mass of the rod and the other associated with the putty. And for each of these, the height is going to be, I'll call it some generic L times 1 minus cosine theta naught, where this generic L would be little l for the putty and L over 2 for the rod. Okay, that's our pendulum geometry result. Please go back and see a previous video where I described the pendulum geometry. So for part 2, we're going to use the total mechanical energy at this point equals total mechanical energy at that point. So rotational kinetic energy at the bottom equals the gravitational potential energy at the extreme swing position. So that's 1/2 times the moment of inertia, which again is that thing here. So it's 4/3 ml squared times omega naught squared equals, this one is mg times the pendulum geometry height. For the putty, I'll write first. It's mgl times 1 minus cosine theta. And then for the rod, it's mgl over 2, 1 minus cosine theta. So let's make a couple simplifications. There's a L that cancels out. So omega naught, however, is that. So let me just waste no time and substitute it. So I get 1/2 4/3 times 3/4. It's squared. So I'll write it as 3/4 times 3/4 V naught squared over L squared. And on this side, I have G plus G over 2, which is 3/2 G times 1 minus cosine theta. You can see that I'm left now with very little. That does not cancel out. I just have a 4 down there if I did everything right. Let me just make sure. Yeah, looks like I did everything right. So I have V naught squared over 4L G, I'll bring the G down here, GL squared equals 1 minus cosine theta. All right, so that gives me, these are all knots because that extreme position I called as theta naught there. So I have the extreme position, and so in a sense I can find the theta naught from here by solving. That's amplitude. Let me write this as cosine theta naught equals 1 minus V naught squared over 4GL squared, and that gives me theta naught, which is the arc cosine of 1 minus V naught squared over 4GL squared. So that's a good intermediate result to have, because that'll tie into our equation there. Now, before we go any further, let's anticipate what we have to write as the equation of the simple harmonic oscillation for this system. Theta of t is going to be theta naught, which I actually have found, times cosine of omega simple harmonic times t. Now be careful, this omega simple harmonic and this omega naught are not related at all, plus some phase constant phi, which we also have to determine in this case. What is omega simple harmonic? Well, that comes from the period of a physical pendulum. So omega simple harmonic is the square root of the total mass of the system times g times d, which is the distance between the center of mass of the system and the pivot point, divided by the moment of inertia about the pivot point. Now actually we have all of these right out there, so let's write it. The total mass is just 2m because it's the putty plus the rod times g. Now the center of mass distance is going to be precisely halfway between L over 2 and L, which means it's going to be at 3/4 L. So that's going to be 3/4 L divided by the moment of inertia, which I've done already 2 times. It's 4/3 ml squared. So that was not too bad. Now observe what happens. This 3/4 divided by 4/3 is actually 3 squared over 4 squared, so I can bring it outside as 3/4. And then I have a √2, which I can also bring outside because there's no reason not to put all the numbers together, times the square root of g over L. That's really nice because that does have the units of radians per second. Now we have found omega, we have to find phi. Now I'm not going to do this because it's exactly like in that mouse jumping off the cheese block problem, except in this, well, you know what? Let me, rather than refer you back to a previous video, let me just do it. If I take the derivative of this, I'm going to get the equation d theta by dt is angular velocity omega equals negative omega simple harmonic times theta naught sine of omega simple harmonic times time plus phi. Let's fix the moment of collision to be t equals 0. So at t equals 0, let's try to find theta of t and omega of t. That will fix the phase phi. So theta of 0 is going to be theta naught cosine phi. Well, the angle was just dangling vertically, so that's 0, which means that phi is going to be either pi over 2 or 3 pi over 2, exactly like in that mouse jumping off the cheese block problem we had there in the previous video. So that omega of 0 now is going to be negative omega simple harmonic times theta naught sine of 0 plus phi, which is just sine of phi. Now, which of these two will result? But this time, remember that omega naught is out of the page. That's the only difference between that cheese block problem, and there the cheese block was going to the left. Here, the rod, the angular velocity of the rod is actually out of the page, so it's positive. So I'm glad I did this. It's a little bit different. So if this has to be positive, it means that sine phi is less than 0. Sine phi is less than 0 means we have to choose 3 pi over 2 instead. So now we have our full-blown answer to this problem. Theta of t is theta naught, and let's brace ourselves. This is not easy viewing. Times cosine of omega simple harmonic, which is that, times the time plus the phase angle. And in this manner, we have solved the problem. But notice there's been some very basic physics. It's whatever physics that you've studied all along throughout this course that has been used one after the other to tackle this problem.